In this video, we are going to discuss domain of a radical function, domain of a radical expression, as well as graphing basic square root and cube root functions. So remember, if the index is even, then the radicand must be non-negative, greater than or equal to 0. We've talked about that square root of a negative number is not a real number. So if you have a negative inside an even root, then your solution is not a real number. So in order for us to have a real output, we need to make sure whatever is inside the even root, only the even root, like square root, fourth root, sixth root, radicand of an even root has to be either 0 or greater than 0. So greater than or equal to 0. If your radicand is 0, that's fine because square root of 0 is equal to 0, which is still a real number. So we want to make sure whatever is inside a square root or fourth root or sixth root or any even root is always greater than or equal to 0. If it's not, then your output will be not a real number. So when we're thinking about domain, domain of an even root, we want to make sure the radicand, whatever is inside the square root or fourth root or sixth root, is always greater than or equal to 0. So to find out the domain of a radical expression even root, plug the radicand greater than or equal to 0 and solve. If the radical is in the denominator, then plug it equal to greater than 0 only, not equal to 0, just greater than 0, because we don't want to have 0 in the denominator. Now we have another domain restriction which we talked about in the rational functions, that you cannot have 0 in the denominator. It makes your whole function undefined. Now, domain of an odd root is a lot easier to deal with because we've seen in an odd root, your answer is always a real number. Even if you have a negative inside, your answer will be a real number. So if you have cube root of 0, that is still 0. So for an odd root, doesn't matter what's inside your radical. What's the radicand? It doesn't really matter. Your domain will be always all real numbers. Unless your odd root is sitting in the denominator of a fraction, then you want to make sure that it's not equal to 0. The denominator does not become equal to 0. So thinking about domain of an even root, plug the radicand greater than or equal to 0. If the radical is in the denominator, plug it only greater than 0, and then solve because we don't want 0 in the denominator. Let's see some examples. Here's example number 1. I always write the answers in the interval notation, but you can also express them in the set builder form. Note for domain problem, give your answer in the interval notation. So I'm going to be seeking interval notation. So here's first problem. Evaluate f of 7 when we are given f of x equal to this. What does this mean? That means we are given f of x is square root of 2x plus 4. F of 7 means we are going to replace the x by 7, square root of 14 plus 4, which is square root of 18. Okay. And further, we can write it as 2 times 9. If we've seen how to simplify the square root, 2 times 3, we can pull the 3 out because we have a pair of 2 3's inside, and it would be equal to 3 root 2. For the next one, we are going to evaluate g of negative 5. So g of negative 5 would be equal to cube root of 2 plus 2 times negative 5, which turns out to be cube root of 2. 2 times negative 5 is negative 10. Cube root of negative 8, which is equal to negative 2, because negative 2 times negative 2 times negative 2 gives me negative 8. Example number 3, find the domain of f of x equals square root of x minus 5. Okay, so it's a square root. We don't want to have a negative inside the square root. So whatever is inside the square root, we want this inside to be always greater than or equal to 0. Because we're dealing with an even root, so no negative inside an even root. only then you will have the real output. If you have a negative inside the even root, your output would be not real. So those items will be not in the domain. So no negative inside the even root. No negative means greater than or equal to 0. We want this to be positive only. So I'm going to add 5 to both sides. So x has to be greater than or equal to 5. How do I express it in the interval notation? Well, to express my answer, I'm going to put bracket around 5 because I want to include 5 in my solution. 5 to infinity. So I can plug in any values of x between 5 and infinity, including 5, and I will still have a real output. Other than this circle domain, other than these circle values, any other value if I put in for x, I will end up with domain restriction. I will end up with a negative inside an even root, and that's not allowed. So next problem, find the domain of cube root of 2x minus 3. We've talked about for the cube roots, domain for cube roots is always domain of an odd root function is always all real numbers, negative infinity to positive infinity. For odd roots, we don't care if you have a negative inside, a positive inside, a 0 inside. It's always going to be a real output. So your domain would be a negative infinity to positive infinity for the odd root. Next, we have an even root again. And again, remember, we don't want to have no negative inside an even root. No negative radicand for an even root. No negative inside an even root. So 2x minus 3 has to be greater than or equal to 0. Let's go ahead and solve it. 2x has to be greater than or equal to 3. X has to be greater than or equal to 3 halves. So here we are. 3 halves to infinity is what my domain is. Infinity always gets parentheses because we don't really know where it is. It just means you can plug in all the numbers that exist in the world starting with 3 halves, including 3 halves. Because if I plug in 3 halves for x, I will have 0 in the fourth root, and fourth root of 0 is still 0, which is still a real number. Any numbers bigger than 3 halves and including 3 halves are okay to plug in to use for x here. They all will give me real output. Any numbers smaller than 3 halves would be not okay, so they would be not included. Make sure you use the correct symbol. Bracket means we are including 3 halves. Okay. Next, find the domain of z over 6th root of 2z minus 4. Well, I do have an even root here, so I don't want to have a 0 inside the even root. No negative inside an even root, so I still want no negative inside even root. And I also don't want to have 0 in the denominator. No 0 in the denominator. That's another issue that I'm going to get into because I have a fraction here. So the 2z minus 4 has to be greater than 0, not greater than equal to 0 like we did in the last case. Okay, so only greater than 0 because we don't want it to equal 0. Let's go ahead and solve it. Z has to be greater than 4 halves, which means z has to be greater than 2. So any z greater than 2 is okay. When I write the domain here, I'm going to not use bracket around 2 because we do not want to include the 2 in our solution. We want anything bigger than 2 to infinity. Parentheses means, notice I'm using parentheses around 2. Parentheses means 2 is not included in my solution. Okay. What happens if z is equal to 2? I will have 0 in the denominator, and that makes my whole function undefined. So you got to be cautious there. Next, we have find the domain of f of x equals square root of x squared plus 3. Here, I do have an even root. I am dealing with an even root problem. So if you have an even root, you want to make sure that inside the even root is always positive. Now, the x squared plus 3 is always going to be positive. X squared plus 3 is always positive, no matter what x is. X can be negative 1, negative 2, negative 100, negative 5,000, anything it wants to be. But when I square it, it will become positive. So x squared plus 3 is always positive. That means we're going to have no worries about any values of x that will get us in trouble means that will give us a negative inside the even root. So there's no issue with that. So x squared plus 3 is always positive. That means my domain will be here, negative infinity to infinity. You can also write it as all real numbers. That means any value of x can be plugged in here, or any value between negative infinity to positive infinity can be plugged in here. We would still have a real output. Because even if your x is negative, x squared is not going to be negative. Plus, when you add 3 to it, you're always going to be positive. Right, next find the domain of root x minus 2. Now be cautious, this negative 2 is not inside your radical, okay? The only thing you have inside your radical is x, and we've talked about that we want the x to be greater than or equal to 0. So any value of x greater than or equal to 0 is going to be my domain here, and it would still give me a real output. So let's start by plugging a 0 in here for x. If x is 0, square root of 0 is 0, minus 2 is negative 2. So if I'm just trying to make a table, if I plug 0 for x, y will be negative 2. If I plug 1 for x, y will be negative 1. So any values greater than 0 are going to be fine, and that's my domain, and this is a bracket, including 0. Let's think about graphing the radical function. So in this video, I'm just going to do some basic graphs, and I'm going to be using the table here to graph the radical functions. Let's just pick some good values of x and find the corresponding y values, plot the points, and connect the dots. So I have a square root of x. I need to think about the domain. Which values of x can I use here? Which values of x are in the domain? Which values are not in the domain? So keep that in mind too. So here we know we have a square root of x. In order for this to give me a real output, because this is a real plane, xy plane is a real plane. In order for me to have a real output, I need to make sure that I don't have a negative inside the radical. Am I okay with 0? Of course. Square root of 0 is still 0. Now I'm going to pick the nice values that give me the nice y value, y output value. If I use x as 1, square root of 1 is still 1. Should I use 2? Square root of 2 is 1.4 something. I don't want to use that because it's going to be a decimal. Next nice value I'm going to use is 4. If x is 4, square root of 4 will be 2. If x is 9, square root of 9 would be 3. Let's go ahead and plot these points, and we'll have our graphs. 0, 0, 1, 1, x is 4, y is 2, 9, and y is 3. There we go. And that's our graph for the square root function. Next, let's go ahead and graph the function square root of x minus 3 plus 5. Okay, I gotta be clever here. I wanna pick the values that give me the nice output, okay? First of all, let's think about the domain in this case. We didn't write the domain in the last case, but it's good to, we talked about it. We said the domain was 0 to infinity. Any values greater than 0 were fine. In this case, we want this x minus 3 to be always greater than or equal to 0. That means we want x to be greater than or equal to 3. So my domain is 3 to infinity. Any values from 3 and above are okay to plug in. If I plug in a 3, do I get a nice output value? Not outfit, sorry. Nice output value. Yeah, if I plug a 3 in, 3 minus 3 is 0. Square root of 0 is 0. 0 plus 5 is 5. So that's still a nice y value. Now, should I plug in a 4? Let's think about 4 minus 3 is 1. Square root of 1 is 1. Yeah, 4 also seems like a nice value to plug in. 4 minus 3 is 1, and I plug 4 in for x. And 1 plus 5 is 6. The next nice value, I want to have nice output values. So next value that will give me a nice output here is going to be 7. Because 7 minus 3 is 4, and 4 is a perfect square root. Square root of 4 is 2. If I plug a 7, I get a 7. 7 take away 3 is 4. Square root of 4 is 2. 2 plus 5 is 7. Yeah, I get 7, 7. So let's start plotting these values. This is my x values and y values. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have space, but I do suggest that if you have space, write them down. You can also use Desmos to check your graph if you want to. So x is 3, y is 5. X is 3, y is 5. X is 4, y is 6. X is 7, y is 7. So something like this. That's how my graph is going to look like. You can also think about shifting transformations on the graph. So this is something new, and you'll discuss a lot more of it in college algebra. So f of x plus minus h plus minus k. So think about your basic parent graph. Parent graph is the square root of x. So this k actually moves up or down. If it's plus k, up, minus k, it will move it k units down. And this h moves it left or right. If it's plus h, it will move it to the left. If it's minus h, it will move it to the right. So my basic parent graph was square root of x. And the k here is 5. So I'm going to move the square root of x 5 units up and 3 units to the right. Okay, k is 5, h is negative 3. So 5 up, 3 to the right. So if I shift my basic graph that I have 5 up, 1, 2, 3, 4, 5, 1, 2, 3, that's how I can also kind of estimate. I didn't move every single point, but we can move them point by point and we'll get the same graph. Okay, next, graphing the cube root function. Well, we already talked about for the cube root function, there's no domain restrictions. You can have all the negative values, positive values, everything is okay. But I just want to pick the nice values that give me a good, nice output to plot easily on the graph. So can I have 0? Cube root of 0 is still 0. Cube root of 1 is still 1. Cube root of negative 1 is still negative 1. Cube root of 8 is 2. Cube root of negative 8 is negative 2. The next nice cube root is actually 27. That's a little too far, but I won't be able to graph it. It's okay to have it on your table. So let's start plotting my point 0, 0, 1, 1, negative 1, negative 1. The next one we have is x is 2 and y. X is 8 and y is 2. 1, 2, 3, 4, 5, 6, 7, 8. And y is 2. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So this is how my cube root graph is going to look like. It goes on forever. And domain here is all real numbers. All real numbers. We haven't talked about the range. Range is the y values. Let's think about the y values range as well. Which y values it's going to take? It's going to take the y values all real numbers as well, because it's gonna grow on both sides forever, and it will be taking all real numbers for the y values as well. Previous graph, if you look at the number 10, the range, the y values it's going to take will be 5 and above. Starting with the y as 5 to all the way to infinity, they will be allowed y values. Let's think about number 9. What's the y values for the range here? The range would be, it's going to take 0 to infinity, all the real y values. Range are the y values, domain are the x values. Input values or x values, they're called domain. Output values or the y values are called the range. Domain is all real numbers and range is also all real numbers here. Let's check out one last example, number 12. Again, you can think of shifting, translating based on what we saw earlier. This is telling me that's going to move the graph 3 units down 3 units. And it's going to move the graph when I have plus 1, it is moved to the left 1 unit. Okay, we can shift our basic graph, the one we did in number 11, we can translate it, or we can also make a table and come up with our points that way. So 3 units down and 1 unit left. We can do that as well, or we can make a table. If I am to make a table, I'm going to pick the nice output values, nicer values that give me the good real outputs that I can plot easily on the graph. So let's go ahead and plug. Is it okay to use 0 for x? Of course, 0 is fine, because cube root of 1, if I plug x as 0, cube root of 1 is 1. 1 minus 3 is negative 2. The next nice value I can plug in is 7. If I plug a 7 in there, that would give me 7 plus 1 is 8. Cube root of 8 is 2. 2 minus 3 is negative 1. The next nice value I can plug in is negative 1. So negative 1 plus 1 is 0. Cube root of 0 is 0. When I plug it in, it leaves me with minus 3. And similarly, you can plug in more values, or you can pick each point on our basic graph, because on my basic graph, these were my points. I had 2 and 8, 1, 2, 3, 4, 5, 6, 7, 8, and 2, 4, 5, 6, 7, 8, and 2. So we can pick each point and move it 3 units down, 1 unit left. So 3 down, 1 left. 1, 2, 3, 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 1 left. Okay. So something like this is how my graph is going to look like. So you can plot the points, or you can translate the actual graph. Remember, if you see something in the form of f of x, f of x plus minus h plus minus k, the k is going to move my graph up and down. H is going to move my graph left and right. This is going to move k units up. If it's plus k, minus k will be k units down. Plus h means move h units to the left. Minus h means moves h unit to the right. Okay, that's all for this video.